Okay, students, welcome to video class 42. And in this video, we are going to do some numerical examples of a state model. And this is what we have studied in the last video. Just a recap of what things that is. The, so in our last video, we have seen the state model. Now, by state model, it refers to two equations. One is the state equation, the other one is the output equation. Now we have seen a state equation. What is a state equation? State equation represents the derivative, the first derivative of the state variables, right? And that will be a function of the state variable and input. And you may just make the correction. I mean, it's not a correction, it is obvious, right? So anyway, all these functions are the functions of time. So you can represent that x dot of t is equal to a times x of t plus b times u of t, where a is the system matrix, b is the input matrix. Similarly, you can have the output equation of the form c into y of t is equal to c into x of t plus d into u of t, where c is the output matrix and d is the coupling matrix. So I'm rewriting, I've rewritten again this. So this set of equations are called as a state model of a system. Okay, so now before going into the numerical and numericals, the state model can be of two types. They are the physical variable model and the phase variable model. It is based on the choice of the state variables. That is, in a physical variable model, that physical variable will be selected as the state variable. For example, in an RLC circuit, which is an energized, say you are applying a voltage across an RLC circuit, that will result in a current. So this I of t can be selected as a state variable. So in that case, such a model we call as a physical variable model. Or there is another thing called as a phase variable model. That is, if you are given with a differential of an output, that output variable, say for example y of t, as we have seen in the previous video, and its derivatives and its successive derivatives, okay, successive derivatives can be taken as the state variable. Okay, so based on this, you can have two different models, that is a physical variable model and a phase variable model. Now there are three important points regarding this phase variable and the order of the system. Say the number of state variables needed to, these are very important points, the number of state variables, okay, needed to represent a system, is equal to the order of the system that we have seen in the last video. Okay, order of the system. Okay, right? I have just given you an example in that we have seen in you can refer this. Say we have considered a second order system, and we have seen that there are two variables x1 of t and x2 of t. So it is equal to the order of the system. Now another point is the number of in an electrical system, that is, if you are going for this physical variable model, this is a very important point. In an electrical system or a mechanical system, the number of energy, the number of variables, the number of state variables will be equal to the number of energy storing devices in that system. Okay, or the number of energy storing elements, you can call that by elements in that system. Okay, say for example, in this circuit you have two energy storing elements, that is an inductance and a capacitance. So obviously this particular system can have two state variables. Okay, right? Okay, so here you have a question. you have given with a mechanical system, and you're asked to obtain the state model of the mechanical system. So whenever you are asked to have a state model, you are actually asked to obtain this matrix. Okay, that is x dot of t and the y of t. That is the state, the first derivative of the state variables used, and the output equation. Okay, so before that, let's have a look at this system. This system is a simple mechanical mass spring damper system with mass m, and a damper is having a damping coefficient b, and a spring with a spring constant k. Okay, now, and at this mass a force is applied, f of t, which is your input, and this has produced a displacement x. So as far this system is concerned, the output is actually your ex, or this can be considered as a physical variable associated with this particular mechanical system. Okay, now how will you start with? The first thing that we need to find out is we need to start with the state variable. So the output variable, or this ex, or the displacement, can be considered. So the displacement ex is considered to be a state variable, and we are assuming that state variable as x1. Okay, so x is equal to, x is assigned to be your x1. Okay, right. Now you can have the derivative of that. Okay, so what will be dx by dt? So dx by dt is the velocity. If x is the displacement, then velocity is dx by dt, or this velocity can be treated as your x1, or this is actually x1 dot, or this is equal to x2, right? This derivative is referred as your x2, right? Okay, so this is it. So this is x1. x1 is assigned as the displacement and its velocity. So I told you that you can have the displacement and its derivative. So this is the variable associated with this. So that is taken as a state variable, that is assigned to be a state variable x1, and the next state variable is the derivative of that, which seems to be the velocity of this due to this displacement. Okay, now to get the further equation, so we have got the first derivative of the variable x1. Now we need to get the first derivative of x2 as well. For that, you need to write down the equation associated with that, the force balance equation. What is that? We have already studied that in our module 1, right? So the force balance equation is given by m into d square x by dt square plus b into dx by dt plus k into x is equal to f of t, right? Or you can rewrite that by what is, okay, let's start from here. So this will be k into x is actually x1, right? So k into x1 plus b into dx by dt, or that is x1 dot, or that is assigned to be x2, and when you take the derivative of this, again if you take the derivative, that is d square x by dt square, or that's acceleration. So acceleration is nothing but it is x2 dot, right? So this is plus m into x2 dot. Now from this you can evaluate, so this is equated to is equal to f of t, or from this you can evaluate x2 dot. Now what will be your x2 dot? So that you will get you can write the next equation as x2 m into x2 dot is equal to, you can bring all these terms to this side, so that this becomes minus k into x1, right? Bringing this to this side, then minus b into x2 okay, then plus f of t, right? So this is it. So what is your x2 dot? x2 dot. x2 dot is going to be equal to minus k by m into x1, right? Minus b by m into x2 plus 1 by m into f of t, right? So you got two equation. One is x1 dot is equal to x2, and other one is x2 dot is equal to this thing. So from this you have found out the first derivative of the state variables that we have assigned. Okay, now from the differential equation of this mechanical system, we have seen that this is the order of the system is a second order, and we have seen that the number of state variables required to represent this is 2 because the order is 2. So we have seen we have assigned x1 and x2 to be the two state variables, and we have derived its first we have found out its first derivative. So this equation gives the first derivative of x1, this equation gives you the first derivative of x2. Okay, now you can have the matrix equation. So right, so the first matrix, that is x1 dot and x2 dot is equal to okay, the first part will be the state variable, so this will be x1 and x2. And what must be this matrix? This matrix, since there are two state variables, this matrix has to be a 2 by 2 matrix. This is a 2 into 1 matrix. Now the result must be, what is this? This is again a 2 into 1 matrix. So upon this multiplication, you need to get a 2 into 1 matrix. So definitely this will be giving a 2 into 1 matrix because this is confirmable. Multiplication is confirmable. Okay, so let us try to write the equation. Look, x1 dot is equal to x2. So there is no x1 or the input part. So this part will be 0. That is writing this equation. x1 dot is equal to x2, meaning, right? So look at this. x1 dot is equal to 0 into x1 plus x2. Now coming to this part, this will be, look at this. This will be minus k by m. So this must be minus k by m, and this is minus b by m. Okay. But this is not complete. Now this, what is this? X dot is of the form a into x of t. So we have completed this part. Now we also require b into u of t. Anyway, looking at the first equation, there is no input side. So okay, so that plus. Now this matrix is actually the you can say consider this matrix as the sum of two matrices. So if this is the sum of these two matrices, we know that the result of this is going to be a 2 into 1 matrix. So definitely the part that comes over here must also give you a 2 into 1 matrix. Then only addition is possible, right? Okay, so this can be represented as, in the first part, there is no, as I have told you, there is no input. So you can multiply this by an input f of t. Okay, f of t into this column matrix. So the first column in the input side, in x1 dot side, there is no input, while in this case you have a 1 by m times f of t. So this is 1 by m. Now look at this. You may just try to write down the equation in this way. So this will be x1 dot is equal to x1 plus 0. That right? x2 dot is minus k by m into x2 minus b by m into x2 plus 1 by m into f of t. Okay, so this is also a 2 into 1 matrix. 2 into 1 matrix into a function. That is again a 2 into 1 matrix. Okay, so this is addition, additive. Okay, the matrix are additive as well. Okay, so this is actually your state equation. Okay, state equation. So this refers to, so this is actually the state equation. State equation. Okay, So that is the first part of the state model. Now the next part is to find out what? Find out the output equation. Now let us see how it is. Okay. Now let's see what is the output equation. Now look at this mechanical system. Now this is the input, and what is the output of the system? The output is actually your x. So your y of t or y is equal to y of t. Okay, right? So you can also add, there is nothing wrong in putting of t. Okay, okay, y of t is equal to, that is the output is equal to x. Now we have assigned this x to be equal to x1. x1 is what? x1 is actually the state variable. Okay, so y of t is equal to x1, right? Now we have already seen that the output is actually a function of the state variable and the input, right? Right, and that has to be of the form y is equal to cx plus d into u of t. But in this equation, you can't find any input side. So what you can do is, but we have already assigned two state variables. So the matrix can be written as y of t is equal to, or this y of t matrix will be of the form 1, 0 into x1, x2, right? Because there is no x2 here, only x1 is there. So this is 1, 0, x1, x2, right? This is very simple. So this forms the output equation, right? And these two equations forms the state model of this particular system. Okay, right? So these two equations comprises the state model. Now look at this, and you can find the differential equation associated with this system is a second order differential equation, and since it is of the second order, it requires two state variables to represent this as a state model, and we have assigned that to be x1 and x2, and we have found out the first derivative of x1 and x2 as well as the output equation. Okay. Okay, now look at this. You have another question, a bit more complex question than the previous question. You have two masses with M1 and M2, and this M2 is subjected to a force, that is the input force is applied at M2, and that results in two outputs, that is two displacements called as y1 and y2. Okay, and these masses are connected to this fixed surface by a damping constant B1 and a spring constant K1, while these two masses are connected with the damper as well as a spring with the damping constant B2 and K2. Now we know that how many state variables you require. Anyway, minimum it requires two state variables because there are two outputs are shown. Okay, so each output have to be assigned as a state variable. Okay, now when you write equation for M1, you can see that that's going to be a second order differential equation, and similarly you can write the equation for M2. That also gives you a second order differential equation. So for each equation, if it is a second order differential equation for this side, for this M1, you can see that that can be represented by two state variables, because how will you select the number of state variables? The state variable depends on the number of the order of that system. So this particular system can be described completely by two sets of second order differential equations. So one of the second order differential equation requires second order differential equation requires two state variables. So since it has got two differential equation, then that will be this particular system will be having four state variables. So we'll start with this. So we can assume this y1 as one of the displacement of m1. Now this y1 can be selected as your the x1. So this is the first standard state variable. Okay. Now, what can you say about the about its derivative? So you can have the derivative, that is dy y1 by dt, or that is your x1 dot, or that can be assigned to be your x2. Okay, so that's the first thing. So we have assigned x1 dot is equal to x2, right? Now what's the next thing? Now you can have, similarly you can have this y2 to be another state variable as x3, and its derivative dy2 by dt, which is actually your x3 dot, or that can be assigned as x4. Okay, right? So x3 dot is equal to x4, right? So from the two masses we have assigned two state variables each. One is its displacement and other its derivative. Now why do you need this derivative? Because you know that when you write the equation for m1, that's going to give you a second order derivative. So let us start with that case of m1. Okay. Now writing equation with respect, equation for differential equation corresponding to this mass m1, you will get this as what? m1 into d square y1 by dt square, right? m1 into okay, then next is plus b1 into dy1 by dt plus k1 into y1, right? k1 into y1, then plus, what about b2? Now b2 is in between two displacements, so this must be what? This must be into d by dt of, since you're writing equation for mass 1, y1 is dominant, so this must be y1 minus y2, right? Plus, what about k2? K2 is also the between m1 and m2, so this must be into y1 minus y2, right? Okay, this already you know how to do this. Now from this you will be able to get x2 dot, right? Because why? Because that is a second derivative of this. Now the first derivative of dy1 by dt is assigned to be x2, so you will be getting from this equation, you'll be getting x2 dot, right? So similarly, if you write equation for this, you will be able to get the equation for x4 dot. So once you get the first derivatives of all the state variables that we have assigned, you'll be getting the state equation. Okay. Now let us see how to obtain your x2 dot. Okay. Okay. Now from this you can have m1 into what is d square y1 by dt square. Now we know that dy1 by dt is assigned to be x2. So this must be your x2 dot. So m1 into x2 dot plus, what is b1? dy1 by dt. dy1 by dt is assumed to be x1 dot, right? That is x1 dot, or that is assigned to be x2. So b1 is into x2 plus, what about k1 into y1? Now y1 is actually assigned to be k1 into x1, right? y1 is assigned to be x1 plus b2 into, okay, b2 into the derivative of y1 minus derivative of y2. The derivative of y1 is assumed to be x2, while derivative of y2 is assumed to be x4. So this must be x2 b2 into x2 sorry x1 yeah x2 minus x4, right? b2 into x2 minus x4 plus k2 into, it is y1 minus y2. y1 is x1 and y2 is x2, so x3. So this will be x1 minus x3, right? Okay, now this is equal to what? This is equal to so this is actually the force balance equation. Now this force balance equation is, so you have written the force balance equation for the mass m1, and that is equated to 0 because there is no applied force as far as this m1 is concerned. So this is equal to 0. Now from this you will be able to get x2 dot. So m1 into x2 dot will be equal to x2 dot will be equal to x2 dot will be equal to so you can bring all these to the other side so that you can write this as k1 minus k1 x1, okay, minus b1 x2 minus b2 into x2 minus x4 minus k2 into x1 minus x3. Okay, now you can separate this x1, x2, x3 and x4 so that, so here you have an x1, so bringing those together you will be able to get this x1 as minus k1 minus k2, right? Then bringing x2, so this will be plus x2 into minus b1 minus b2, right? Then what about x3? You have an x3 over here, so this will be plus k2 into x3 plus k2 b2 into x4, right? And so this is actually your m1 x2 dot. So what must be your x2 dot? x2 dot will be 1 by m1, 1 by m1, right? This is divided by m1, this is divided by m1, right? So this is actually your x2 dot. Okay, so we have assigned x1, x2, x3 and x4 as the 4 variables. So that means you need to get x1 dot, x2 dot, now x3 dot we already know, and we also now require x4 dot. Now how will you get x4 dot? Now you will be getting x4 dot when you write equation for m2. Okay, now similarly you can write equation for m2 as m2 is equal to d square y2 of t by dt square. Okay, now then you have b2 into the derivative of your writing equation for m2, derivative of y2 of t minus y1 of t, okay, plus k2 into y2 of t minus y1. Now from this you can assign this value. Now from here, what is y2 and y1? y2 and y1 is assumed to be x1 and x3, assigned to be x1 and x3, and the derivative of x1 and x3 is assigned as x2 and x4. So you can call this as b2 into x4 minus x2, right? The derivative of this b2 into, and m2 will be m2 into d square by 2 of t. We have already assumed dy 2 of by dt as x4, so the second derivative of this will be x4 dot. So this is assigned as x4 dot. Now from this equation we will be able to get x4 dot. So that means b2 into x4 dot. Now you can bring this, you can bring this terms to this side, so we'll be getting this as minus b1 into x4 minus x2, x4 minus, this is x4, x4 minus x2 minus k2 into x3 minus x1 plus u. Now rearranging, you will be getting like this, an equation like this. So you may just do it by yourself. So that this is x4 dot, this is m2 into x4. So you should divide that by m2, this by m2, this one by m2, and this one by m2, this one by m2. Okay, so you got an x4 dot. Look at this. So how many boxes? So one is x1 dot is equal to x2, second one is x2 dot is this much, x3 dot is equal to x4, and the fourth one is x4 dot is equal to this thing. Now you can have the matrix equation, a big matrix x1 dot, x2 dot, x3 dot, and x4 dot, right? Which is equal to a very big matrix, right? This must be a very big matrix, into x1, x2, x3, x4. And what must be the size of this big matrix? Since there are 4 variables, this must be a 4 into 4 matrix, right? Now coming to the first equation, x1 dot is as x2. So in the first row, you will be having only values corresponding to the x2, right? All the others are 0. Now coming to the second, that is x2 dot. x2 dot is, right, x1 into minus k1 minus k2 by m. So what is the coefficient of x1? So the coefficient of x1 will be minus of k1 plus k2 by m1. Now what must be the second one? Minus of b1 plus b2 by m. The third one is k2 by m1. The fourth one is b2 by, so you can rewrite that using that expression. You can have this. Now what about x3 dot? x3 dot is equal to x4. That means you have only terms x4, so this will be 0, 0, 1. And what will be the last term? x4 dot, k2 by m2, b2 by m2, then next is minus k2 by m2, and minus b2 by m2. Okay, now is it finished? No, you have one more term, that is u by 1 by m2. Okay, so u by 1 by m2. So you can have a column matrix into u. There is only one input, that is into u. But for each equation, now when you look at x1 dot equation, x2 dot and x3 dot, you can't find any u, right? So that means these 3 equations are independent of u, or the coefficient associated with that u will be 0, 0 up to third row, and the final row will be having 1 by m2. Okay, right? So this is it. So this one is actually called as the state equation of that system, right? Now what can you say about the output? Now it is left to us. See, this y2 and y1 both are outputs. Now I mean, you can just specify that as, say, this suppose you can either take y1 or y2 as output, right? Here y2 or y1 as output. Now I'm giving the input here. So if this is the displacement I am concerned with, or this is the output I am concerned with, then you can write the equation as y1. y1 is your output. Now what is y1? y1 is assumed to be x1, right? Is assigned to be x1. So what must be the expression for y1? The output equation y of t will be equal to 1, 0, 0, 0 into x1, x2, x3, x4. Okay, there is no input, right? Only the y is assigned as the state variable, no input. So this is plus 0, right? So this is 1, 0, 0, 1. Now suppose if y2 is taken as the output, then this equation will be, what is y2? y2 is x3. If y2 is taken as, then 0, 0, 1, 0. This will be x1, x2, x3 and x4. Okay, so this is the output equation. So normally why we took y1 as output means because we have applying the input at m2 and assuming that y1 is your output. Okay, so these two can be your output. So you can write equations anyone as the, you can consider anyone as the output. Okay.